Hello, we will now talk about the different types of inference in AP Stats, which goes along with the Barron's book topics 11 through 13. And there's 13 different types of inferences that you have to be able to do. And this is in essence, 35% of the AP Stats exam is the material that I'm just going to kind of quickly summarize on this video. So anyway, so here's the 13 types of inferences that you have to know how to do. The one proportion z-test z-interval, two proportion z-test z-interval, one sample t-test, one sample t-interval for a mean, two sample t-tests, two sample t-intervals, and then we have our chi-square goodness of fit, chi-square test of homogeneity of populations, chi-square test of association, and then our two linear regression, the t-test and the t-interval. I'm not going to do the linear regression ones right now. We did those at the very end of the school year. So keep in mind, let me remind you, whenever you're asked to make an interval, you got to do four things. You've got to state the type of inference, state what type of interval you're making. In other words, state one of these names, whichever one you're doing. You have to verify your assumptions, which is sin. All right. You have to do the mechanics. In other words, make the interval, and you've got to state your ending. So, which is to interpret the interval in context. In other words, say I'm 95% confident, or whatever your confidence level is, that this interval captures the parameter or captures the difference. So there you go. And that spells out the acronym TAME. Every time you do an interval, you've got to do those four things. Every time you do a test, you got to do five things. You have to do those things, except for you also have to state your hypotheses. The type of interval, type of inference up here, whichever it is, whichever of those 13 things it is, you've got to write one of those 13 things. State your hypotheses, your null and your alternative hypothesis, defining any parameter that you have. All right. Verify your assumptions, which is sin, okay, for the most part. That kind of gets refined depending on the inference. And then do the mechanics, which means find the test statistic, and the p-value. And if it's a t or a chi-squared, you got to state the degrees of freedom. And then state your ending, which means state your decision that you're making with your p-value to reject or fail to reject the null. And whether or not you have convincing evidence for your alternative, which you state in context, and make sure and mention the p-value and compare it to your alpha. So that's what I'm going to do. Now, I'm not going to thoroughly explain all of these, but I want to go through examples of really the first. All right, so the first 11 of these, I want to go through and talk through examples of these, just to kind of give you a quick summary of them. So kind of one of the hardest parts of it is identifying which one of these you're doing. So anyway, so here we go. So let's look at the first problem. So our first problem, by the way, this is topics 11 through 13 in our Barron's book. But so the first problem says this. It says a worker takes a simple random sample of 12 peaches from all the peaches at a farm. The weights are shown below. Perform a two-sided hypothesis test to see if there's evidence that the mean weight of all the pairs differs from 19 ounces. Also create a 95% confidence interval. So, and remember, whenever it says when you're working with a mean, you're doing a t inference, okay? And it says do a test, so that is a t-test. Okay, so, and there's just one sample. So it's a one sample t-test is in essence what we're going to do. And we'll do the interval in a second. So I wrote number one out completely. I'm not going to ask you to take notes on all of these examples. So most of them we're going to talk through, but I wanted to write out at least one of them. So you always state, we're doing the same acronym. You just state your type of inference. This is a one sample t-test for a mean. State your hypotheses. Your null hypothesis is just whatever's claimed in the problem, whatever you're testing against. Your alternative is what you suspect might be true. And we're just testing to see if it differs. It didn't say greater than or less than. So that's that. And define your parameter. So mu is the mean weight of all the peaches at this farm. Okay. So then you sin. So you sin. That's here. And this is the interval. We're not worrying about that right now. Well, anyway. All right. So it says an SRS was taken. The random conditions met. That is going to be a condition for every inference. All 13 of them. That is always a condition. It's also always a condition if you've had sampling without replacement, that your sample size has to be less than 10% of your population size. So you would say that. Just take your sample size is 12, multiply it by 10, and you'd say there's got to be at least that many members of the population. And then, and in this case, all right, so with a mean, so then we have to have normality. In regards to a mean, is our sample size bigger than 30? It's not. Does it say in the problem that things vary approximately normal? It doesn't. If either one of those things to be true, you would say, you know, it says it varies approximately normally, so normality is met. If not, if you don't have those two things, then you graph the sample data, which I did here. Okay, I just made a dot plot for each of those numbers. And as long as there's no outliers or strong skewness, you're going to say normality is reasonable. So there you go. That's kind of the hardest part of it. All right, so then we're going to create our test statistic. All right, so, and let me show you how to do this with your calculator. So doing it by hand, by the way, and you do need to recognize this formula for a multiple choice situation. So to find your test statistic, every test statistic is in essence statistic minus parameter over standard error. Well, our statistic is our X bar. It is the mean of these numbers. So I just entered these in list one and found the X bar. So your parameter is mu. We don't know what mu is, but we're going to use 19 in its place since we're doing this whole thing assuming the null is true. And then there's your standard error. And so the formula for standard error, let me remind you. So standard error for a mean, standard error for mean, there it is, S over the square root of n. And so that's how I got that, and that's how I got that value. And then you can use TCDF to find your p-value. All right, but let me show you how to do this with your calculator. So with your calculator, what you're going to do is we're going to put these in list one. So I'm going to go stat and edit, and I'll put everything in list one. And so the way you do your mechanics with this is we're going to do a t-test. So we're going to go stat, we're going to go test, we go t-test right there, option 2. This time I entered data, so I hit enter on data. My null hypothesis value is 19. I put the data in list 1. Frequency, put a 1 in it. All right, my alternative was not equal to, and I do calculate, and there we go. So there's my test statistic, and there's my p-value right there. And the degrees of freedom for a one sample deal is your sample size minus 1. So our degrees of freedom is 11. And so that's that. And then, so then you're ending, you draw your conclusion with your p-value, which hopefully you're good at by now. This p-value is greater than our alpha of 0.05. So you use 0.05 if you're not given the alpha, which we weren't. So I failed to reject the null hypothesis. There is not convincing evidence that, and then you restate the alternative in context. So you would really need to, I encourage you to write this out as opposed to writing it like this. We do not have convincing evidence that the mean weight of all the peaches at this farm is not equal to 19 ounces. There you go. So that's a one sample t-test. Now to do the t-interval, you would, and I'm not going to write all this out again for the interval. I just did the interval in the ending. You would say, okay, this is a one sample t-interval, all right, for a mean. All right, this would be in essence the same. This would be the same. The sinning would be the same. You wouldn't have hypotheses. There's your mechanics. Okay, now to find the equation for a interval is, there it is. It's statistic plus or minus critical value times the standard error of the statistic. And so there's our statistic. That's our X bar. That is the average of these numbers. Okay, I just average these numbers. There's the formula for standard error, which we found. And how do you find your T star? Well, you could get it off of a table. So we want, this is a 95% confidence interval. And so you go to the table, table B, T distribution critical values, go to 95%. So at the bottom, you go to 95%. And you go up here until you get to your degrees of freedom, which is 11. So 11 right there. So I go over here. And so there's my T star critical value, 2.201. Or you could use inverse T. So now inverse T, if 95% is inside the interval, it means 5% is outside the interval. And so what I'll do is inverse T. So if 5% is outside the interval, I divide that by 2.5% on each tail. So I'm going to do inverse T with 2.5%. So I do inverse T with 0.025, degrees of freedom 11. Okay. So once again, to get the area, you just subtract 95%, 0.95 from 1 and divide it by 2. And that's going to be your area. And that gives you actually a little more exact value of your T star. And it's positive. You just make that positive. So there we go. But Now, doing the interval with your calculator, this is what you would do. So you would go doing your mechanics with your calculator. That's doing it by hand. You just have to write the interval here. Okay, so you could do this. You go stat, you go test, and we go T interval, option 8. So I hit enter. I enter data in list 1. We go 95%. I go calculate. And so there's my interval. And so all you have to write is the interval, and you need to write the degrees of freedom too, sorry. So degrees of freedom is equal to 11. Anytime you do a T interval or T-test or chi-squared, you got to put the degrees of freedom. And then your ending is going to be, I'm 95% confident that that interval captures the parameter mu, and you say what mu is, the mean weight of all the peaches at the farm. Okay, so there you go. So that is a one sample T-test for a mean and one sample T interval for a mean. Let's go on to number 2. So in regards to number 2, I'm not going to write all of these out this time. I'm going to kind of talk through them and show how you do them with your calculator. All right, so a worker takes a simple random sample of 200 peaches from a farm and finds that 38 are rotten. Does this provide statistically significant evidence at alpha is 0.01 that the proportion of all the peaches that are rotten differs from 11%? Okay, perform an appropriate test. Okay, so we're dealing with a proportion here. And when you're dealing with proportions, all right, so this is going to be a z-test and a z-interval. So we perform a test and it says also create the interval. So to do the z-test, so what we would say here is we would say, first of all, this is a one proportion z-test. Our null hypothesis is just going to be that p is equal to 0.11 because that is the claimed value. And then the alternative is p is not equal to 0.11. And you would define p. P is equal to the proportion, and you would write all this out, the proportion of all the peaches that are rotten at this farm. Okay. Now, and then you would send, just like we did up there, it says an SRS was taken, so random conditions met. There must be, and then the I, there must be at least 2,000 peaches at this farm for our sample size to be less than 10% of our population size. And then for normality. Okay, so for normality, remember, in regards to this, we need n times p and n times 1 minus p to be greater than or equal to 10. And since we're doing a hypothesis test, we use 0.11. Okay, so our sample size is 200 times 0.11 and 200 times 1 minus that, which would be 0.89. Both those are bigger than 10. Okay, both those are bigger than 10. That's like 22 and that's like 178 or something. They're both bigger than 10, so normality's met. That's what you would say there. All right, now to create, to find your p-value and test statistic, this is what you would do. So you would go stat, you would go test, and you would go one proportion z-test right there, option 5. So we hit enter. Our null hypothesis value is 0.11. Our alternate, and so then our data is, our sample data is we had 38 out of 200. So we get there. Now, they could have just given you the proportion. 38 out of 200 is 19%. So they could have just said, we took 200 peaches and we found 19% of them, in which case to get X, you would have to say 0.19 times 200. So like that, which is 38. So these have to be integers and N has to be bigger than X. And then we hit calculate. And so there we go. And that is a very small p-value. So there's our test statistic p-value. And so we would, and so there's our test statistic p-value. And then we would say, so we would say that this p-value is less than 0.01. So I reject the null. I have convincing evidence that the proportion of all the peaches that are rotten is not equal to 0.11. All right, so to make the interval, I'm going to go stat, I'm going to go test, and this is a one proportion z interval. So one proportion z interval is down there, right there, option A, one proportion z interval. And so it's 38 over 200. My null hypothesis value is 0.95. I calculate, and there we go. And so you would say, which that's not what I got there. What did I do? Oh, I did the wrong confidence level because you're supposed to do 99% confidence. Okay, so we would go stat, we would go tests, and by the way, well, you'll note that interval I just made with 95% confidence was smaller than this interval. So the more confidence you have, the wider your interval. That's sort of important to know. But anyway, one proportion Z interval. And so we go 99% is what it asked for. Yeah, be careful about that. That's sort of a common error. Pay attention to your confidence level. So we go calculate, and there's the interval. And we would say the ending would be, I'm 99% confident that interval captures P, the proportion of all the peaches that are rotten. Okay, so that's a one sample test and interval with a mean. This is a one sample test and interval with a proportion. All right, so now let's do the two sample stuff. And so now with these, once again, I'm not going to write, I'm going to just sort of talk you, through this. Okay, so let's see what we have here. So this says, is there a difference in the mean weights of the bears in the Georgia forest than the bears in Alabama forest? Okay, so we got two populations here, and it's means. So means, we know it's T, and we appear to have two populations. So this is probably going to be a two sample T test, two sample T interval. All right, Sven takes an SRS of 50 of the bears in the Georgia forest, gets a mean of 540, standard deviation of 60. He takes another SRS, so we do have two samples. Another SRS of 40 bears in the Alabama forest, gets a mean weight of 515, standard deviation of 80. Perform a two-sided test. That means our alternative is going to be not equal to. All right, and then also create a 95% confidence interval for the difference. All right, so this is a two-sample t-test for the difference in means. Remember, if it's a mean, it's T. If it's a mean, it's T. So Mr. T is mean, all right? And so, our null hypothesis is going to be that our two population means are the same. And you would define these. Mu sub G is the mean weight of all the bears in the Georgia forest. Mu sub A is the mean weight of all the bears in the Alabama forest. You would then sin. It says SRSs were taken, so independent random condition is met. Whenever you got two samples, it's independent random. All right, both your population size, you multiply these by 10. There has to be at least 500 bears in the Georgia forest and 400 bears in the Alabama forest for our little n's to be less than or equal to 0.1 times our big n's. And then lastly, normality. So both our sample sizes are bigger than 30. So by the central limit theorem, normality is met. And that's all you've got to say there. Now to do the mechanics, so let me go ahead and do this with our calculator. So to do this with your calculator, so this is a two sample t-test. So I'm going to go stat, I'm going to go test, and two sample t-test. There it is, two sample t-test, number 4. So I hit enter. Now I'm entering stats in this case. In that first problem, I entered data in list 1. But in this case, I don't have the data. I don't have the listed numbers. So I got to go stats. My first mean, so in Georgia, the mean is 540, and the standard deviation is 60, and the sample size is 50. All right, with the second sample, the mean is 515. The second standard deviation is 80. And the second sample size is 40, right like that. The alternative here, notice it didn't say we suspect that Georgia is more than Alabama or Alabama is more than Georgia. So we got to go with not equal to, and it's not considered ethical to look at the sample values and to say, well, Georgia's bears weighed more in the sample value, so I'm going to go with greater than here. You're not supposed to do that. So this is a two-sided test. You always say no to pooled when your calculator asks you to pool. And so you hit calculate. And so there is our test statistic p-value in degrees of freedom. Remember the two sample deal, your degrees of freedom has a complicated formula that you can just get off your calculator, or if you don't have a calculator, just use the smaller sample size -1. And so you would say your conclusion, this p-value is greater than 0.05. So I failed to reject the null. I do not have convincing evidence that, and you'd restate this in context, the mean weight of the bears in the Georgia forest is not equal to the mean weight of the bears in the Alabama forest. That's how you do a two sample t-test, okay? So anyway, and so to do a two sample t interval, so here we go. And so this is gonna be stat, test, and go to two sample t interval. So two sample t interval right there, option 0, we hit enter. Stats, notice that the calculator already went ahead and entered the data for me with the test. My confidence level is 95%, so I go 0.95. I always say no to pool and calculate. And so we would say, I'm 95% confident that this interval captures the difference in mu's, okay? Ordinarily, we say we're 95% confident this interval captures the parameter. But when you got two parameters, when you got two mu's, you're going to say, I'm 95% confident this interval captures the difference in the mu's. Okay. And it's of note, an important connection that you need to be able to make between the interval and the test. Notice when the two sample deal, zero's in the interval. So therefore, it is a plausible value for the true difference. And so you would not expect to reject it. And sure enough, we didn't reject it in the test. And so similarly with these other things, that works to a two-sided test, okay? If these other things, you'll notice, like in this first one, we did not reject the null. So that's basically saying here that 19 is a plausible value and shouldn't be rejected. So we would expect it to be inside the interval, and it is inside the interval, right? And similarly down here, so we rejected the null. So we're saying 0.11 is not a plausible value, okay? So it should not be in the interval, and it's not in the interval, okay? So it's not a plausible value. That's the connection between the p-value, the hypothesized value, and the interval. And remember the connection between the confidence level and the p-value, or the alpha value. 99% goes with an alpha value of 0.01. If it's in the 99% confidence interval, the p-value would be above 0.01. If it's not in the 99% confidence interval, the p-value would be below 0.01, which it certainly is here. So, so there we go. All right, number 4. So number 4 says this. So number 4 says, is there a difference in the proportion of male employees at a company that are satisfied with their jobs and the proportion of female employees at the company that are satisfied with their jobs? So we got two proportions. We got proportions, so we know that's going to be, if we're doing an inference, we're going to do a z-test or a z-interval, okay? And there's two of them. So it's either going to be a two-proportion z-interval or two-proportion z-test. He takes, or maybe both. All right, he takes an SRS of 400 males and 312 females, he takes an SRS of 400 males and finds that 312 of them are satisfied with their job. Takes another SRS of 450 females and finds that 378 of them are satisfied with their job. And this doesn't have instructions as far as what we should do. So this should say, do a test and make an interval. So let's do the test. So this is what is known as a two-proportion z-test, is what it is. Our null hypothesis is going to be our population portions are the same. So P sub M is equal to P sub S. In other words, the proportion of all the males at the company that are satisfied with their job is equal to the proportion of all the females that are satisfied. And the alternative, once again, is not equal to. It doesn't say we suspect one is greater than the other, so we go with not equal to, okay? And you would make sure and define your parameters. You would then sin. So SRSs were taken, so independent random conditions met. You'd say there's got to be at least 400 males and 400, and there's got to be at least 4,000 males and at least 4,500 females at this company for our little n's to be less than or equal to 0.1 times our big N's. Normality, n times p, n times 1 minus p, be greater than 10, and you would use the pooled p hat, which I won't get into here, but the pooled p hat to calculate that. But so let's do this. Let's do this. Let's do the test. And so this is a two-proportion z-test. So here we go. Stat, test, two-proportion z-test, number 6. So we hit enter. And so the first one is I have 312 successes out of 400 trials. So that's 312 out of 400. And the next test, we have 378 out of 450. So I go 378 divided by 450, like that. The alternative is not equal to. We do calculate. There's my p-value and test statistic. And so I would, that's the two things you have to write in your mechanics. And so you would thus say this p-value is below 0.05. So I reject the null. We have convincing evidence that the proportion of males in this company that are satisfied is not equal to the proportion of females in this company that are satisfied. To make the interval, so we would say stat, we would go test, we go two proportion z interval. So two proportion z interval, where is that? It's option B down there, right there. So we go like that. Notice it went ahead and already entered it for me since I just did the test. And it says 95%. Well, it didn't say. I'll make a 95% confidence interval. So, and it's that. And so we would say, our conclusion, we are 95% interval. That interval that this interval captures the difference in population proportions, the difference in P sub m minus P sub f. And so there we go. And so you'll notice the p-value was below 0.05. So we're expecting 0 to not be in the interval. 0 should be rejected because 0 is effectively the null hypothesis value here. Okay, the other way of writing this null hypothesis and alternative would be that P sub m minus P sub f is equal to 0. And the alternative would be P sub m minus P sub f is not equal to 0, just subtracting P sub f from both sides there. And so effectively the null hypothesis is 0. If the null hypothesis value is not in the interval for a two-sided test, then it should be rejected in the test, okay, with the related alpha value. So this instance is 95% confidence. That is related to an alpha of 0.05, okay? If it's not in the 95% confidence interval, the p-value be below 0.05 if it's a two-sided test, which this is. If it was a one-sided test, by the way, you divide the alpha in half. So anyway, okay, great. All right, a couple of more. And so this is going to be, well, we got 3 more actually. Okay, so let's look at this one. So here's a chi-squared one. Okay, chi-squared one. So let's look at this. How do we know it's chi-squared? Because we got categorical variables. Okay, and there's 3 options, not 2. It's not just one proportion. All right. In past years, the percent of desserts ordered at the Skinner confectionery shop has been 48% pies, 36% cakes, and 16% pudding. A worker wishes to see if this will change. He takes a simple random sample of 150 customers, finds that 82 will want pie, 28 will want cake, and 40 will want pudding. Is there statistically significant evidence that the dessert percentages have changed? Okay, perform an appropriate test. This is a categorical situation with 3 options. And so when it's categorical situations, all right, you're going to do a chi-squared. Okay, now if it was just 2 options, if it was like pie or not a pie, okay, if it was binary, you could do a proportion, okay, test like we just did, a 1 proportion z-test. But when you have it divided up into 3 options like this, you have to do chi-squared. This is what we call a chi-squared goodness of fit test. So chi-squared goodness of fit. Your null hypothesis is always going to be the stated proportions. And define these. P sub p is the proportion that want pie, P sub c, proportion that want cake, and P sub p is the proportion that want pudding. For all of this group, okay? For all of the orders at all times at the Skinner confectionery shop, okay? And the alternative, by the way, is at least one of these is wrong. So the alternative, at least one of these is wrong. You would then sort of sin, but not, we don't have normality with chi-squared. Remember with chi-squared, your large counts condition, in essence, all the expected counts have to be greater than or equal to 5, okay? Don't say the word normal. These 2 are the same. You have to have an S. It says SRS was taken, so random conditions met. There must be at least 1,500 customers here for our little n to be less than 0.1 times our big N. And so to do the mechanics, this is what you've got to do. You put your observed counts in list 1. So you're going to go stat and edit. So in list 1, let me clear this out. So in list 1, I put the observed counts. The observed counts have to be integers or you're going to get an error. So he finds that 82 want pie, so we have 82. So hit enter, and then 28 say they want cake, so that's 28. And then 40 say they want pudding, so there we go. The expected counts. What are the expected counts? It is just each proportion times the sample size. How many of if the null is true, if this really is true, how many are you expecting to want pie? Well, 48% of the 150. So you're just going to say 0.48 times 150, right like that, okay? Enter. And so it happens to be an integer. Don't round it if it wasn't an integer, by the way. All right, so your next one is going to be 36%, 0.36 times 150. So the next expected count is 54. And then lastly, 0.16 for the pudding times 150. So we're expecting 24. And so you would, in your conditions, you would have to write those 3 values. All the expected counts, and that would be 72, 54, and 24. You have to write them there, okay? Or if they're written in the problem, say expected counts shown above and circle them up above. They're greater than 5. And that's it. That meets that condition. Don't say the expected counts are greater than 5, thus normality is met. Then you count it wrong. Just say all the expected counts are greater than 5 for any chi-square test. Okay, now we can do the test. So this is how you do it. I've entered the proper things in list 1 and list 2. So I'm going to go stat, I'm going to go test, I'm going to go chi-squared goodness of fit test. Boom, right there. Okay, right there, chi-squared. And so I hit enter. My observed I put in list 1. The expected in list 2. Degrees of freedom for a goodness of fit is the number of categories minus 1. We have 3 categories. So the degrees of freedom is 2. And so we hit calculate. And there it is. You write down those 3 values in your mechanics. So that is a huge chi-squared. In other words, there appears to be a big difference. The sample values appear to really differ from these proportions. And if you think about it, like in our sample, the pies is like over 3 times the cakes, when that percentage is not anywhere near 3 times that percentage. So that's I think the big difference. So your p-value is 4.61 times 10 to the negative 6, which is approximately 0. There's your degrees of freedom. So thus you would, just like, let's do our p-value statement. Can you say it with me? This p-value is less than 0.05. So I reject the null. We have convincing evidence that at least one of the above proportions about desserts is wrong. Make sure and mention the context, please. Okay. So just like every other p-value statement, p-value is low, you reject the null and say you have convincing evidence for the alternative. You just restate your alternative. Okay. In context. All right. That's it. That's how you do a chi-squared goodness of fit. These C and TRB, those are your contributing parts to chi-squared. And so that tells you how much each the cakes or the pies contributed that much, which is not that much. The cakes contributed 12. That's a lot. And then the pudding contributed, and so this would be like PU for pudding, by the way. Okay. And so it contributed a lot as well. In other words, there was a big relative difference with the cakes and the pies. So if you go back and look at the observed and the expected, I mean, look how different. See, I mean, the pies weren't that different as far as the observed and the expected, but these were really a lot different relatively. So that's what's going on there. Now, the formula for chi-squared, which there's only so many things I can talk about, but there it is. There's the formula for chi-squared. If you're doing this by hand, you would take each of these observed counts and subtract the expected counts, square them, and divide by the expected. And you do that for all 3 of these cells, all 3 of these situations, and then add it up, and that gives you the chi-squared. And then and we'll practice getting a p-value with a chi-squared. All right, so then we have this. So we've got this, and so this says 274 voting age people in a city were randomly selected and surveyed. Do the sample data below show evidence of an association, there's a key word there, between gender and political party affiliation? Okay, so and when you look at the males and females, does there appear to be a relationship or an association between gender and political party? So I guess when you look at this, you may say, well, the males amongst this group are more likely to be Democrats and the females are more likely to be Republicans. So there does appear to be a relationship. There does, just eyeballing this, there does appear to be an association, but is it to perform a test? It's not, is there a difference? Is there a statistically significant difference? Or is it plausible that this difference that we see here is just due to sampling variability? Well, you notice this is categorical data, okay? These numbers are not quantitative numbers. They're categorical numbers. They're counts in categories, okay? And so that means chi-squared with this matrix. And so we're going to do a chi-square test, and it's a 2-way table. So we're going to do a test of an association. If it had said, is there a difference in the males and females in regards to political party affiliation? If there's a difference, that'd be a chi-square test of homogeneity, and in which case there would be 2 samples. Like in this one, there's just 1 sample. So if it's 1 sample, that's a test of association. 2 samples would be a test of homogeneity. And so this is what we call a chi-square test of association. Okay, the null hypothesis is that there is no association. There is no association. There's no association, and say your variables between gender and political party affiliation amongst Where did they randomly select these people? Amongst the people in this city, because that's who we can infer about, because that's where we got, that's where these people were randomly selected. So there's no association between gender and political party affiliation for the people in the city. The alternative is there is an association. There is an association between gender and political party affiliation for the people in the city. Okay, you would then, you would then do, do this. It says a random sample is taken, so random conditions met. There has to be at least 2,740 voting age people in the city for our little n to be less than or equal to 0.1 times our big N. All the expected counts can be bigger than 5. And your calculator is going to tell you those. All right. So this is what you do for this. We're going to put this in a matrix, okay, this 2A table. Whenever you do a chi-square test of association or homogeneity, you're going to put it into a matrix. So we're going to go, well, let me quit out of this. So we're going to go second matrix, which is right above the x to the negative 1 button, right below the math button. So second x to the negative 1, which is matrix. And I'm going to go edit matrix A. So I hit enter. This has 2 rows and 3 columns. So I go 2, enter 3. So that's 2 by 3 and hit enter. And so then it's 56 and I just enter those numbers. 71 and 42 and 42 and 33 and 30. Let me make sure I entered those right. So I believe I did. And so all we got to do to get our mechanics now is to do our chi-square test. So we hit the stat button, we go to tests, and we go scroll all the way down to chi-square test. Not the goodness of fit one. That one uses lists. This chi-squared option C uses matrices. And it's going to, all right, so the observed counts I put in list 1. The expected counts, it's going to automatically create them for you and put them in B. And so we go calculate and we got boom. All right, so there we go. There's my chi-square test statistic. There's my p-value and degrees of freedom. And so that's all you have to write in your mechanics. And then your ending, just like all these other p-value statements, this p-value is greater than 0.05. So I do not reject the null. I do not have convincing evidence that, and then you restate the alternative. I do not have convincing evidence that there is an association between gender and political party affiliation for the voting age people in the city. And so that's that. Now, let me remind you in regards to the chi-squared with a 2A table. Okay, you need to write down your expected counts, okay? You have to write down your expected counts. Well, now you can go back and look at matrix B. So if you go second matrix and then just go to edit matrix B, I think is the easiest way to do it. So you hit enter, and then you have to write down those values in your conditions or your assumptions. Okay, and don't round them, please. All right, so you have to write them like that. And the way those were calculated, by the way, just is that for every expected count for each cell, you would take the row total times the column total divided by the table total. So you have to do that for all. That's certainly a bit tedious. Your degrees of freedom with a 2A table is the number of rows minus 1 times the number of columns minus 1. So this is 2 by 3. So you subtract 1 from each of those, and that would be 1 times 2, which is 2. And so that's that. All right. And then the last test I wanted to do with you is known as a matched pair t-test. All right, let's look at this. A study is done to see if a new blood pressure medication works better than the one that's currently on the market. 30 subjects who had high blood pressure at the beginning of the study volunteered for the study. They were randomly assigned to be given the new or the old drug, and their improvement in blood pressure was noted. Then their blood pressure was allowed to go back to its original numbers. They were then given the other drug, which they had not taken. All right, the difference in the improvement, new minus old, was noted for each subject. All right, the mean difference in improvement was 2.3 and a standard deviation of 5.4. Perform an appropriate test to see if there's evidence that the new drug works better. So this is what we call a matched pair situation. In this case, every person is a matched pair because every person is taking both treatments. Okay, that is a popular medical situation where they want to see if one drug works better than another. So they have them take one drug and see what happens, let them go back to what their condition was before, then they take the other drug and see what happens. And the randomness comes in which one they take first, which is key that you do that, just like they described here. And so we have, in essence, we got 30 people doing this. So we've got 30 values. We got 2 values for each person that we're subtracting. And so when you have a match paired situation, you're going to do a t-test, a one sample t-test with the differences. And so that's what we'll do. Our null hypothesis is that there's no difference, that the mean of these differences is 0. The alternative is greater than, because it says, is there evidence that the new drug works better? In other words, there's more improvement with the new drug. And we're taking, it clearly said new minus old, okay? So if there's more improvement with the new, then the mean should be greater than 0. All right, and so to get your mechanics on this, of course, you would send, just like we talked about several times previously. So what we'll do is we'll do a t-test. So we go stat, we go test, we go t-test, like that. And so in this case, we're entering stats. Our null hypothesis value is 0. All right, the mean of our differences is 2.3. So I enter 2.3. The standard deviation of our differences is 5.4. And then our sample size is 30. Our alternative is greater than. And so we hit calculate, and there it is. And there's our t-test statistic and our p-value. And so your degrees of freedom, just like with the one sample thing, be sample size minus 1, which is 29. So our conclusion that we would reach is this p-value is below 0.05. So I reject the null. We have convincing evidence that, and restate the alternative, the mean of the differences of the new minus the old drug, mention the context, is greater than 0. In other words, it appears the new drug works better. That's what that is saying. And then the last thing I wanted to do with you is I wanted you to be able to find p-values given test statistics, okay? If you're given a test statistic, like if you're given a z-test statistic, how do you find a p-value, first of all? Well, you're going to use CDF functions. We're going to use normal CDF. So CDF functions tell you p-values. Tell you p-values, okay? But anyway, so if it is z, it's normal. Normal PDF. Normal CDF. And you're going to use, if it's a z-test statistic, you're going to use mu is equal to 0 and sigma is equal to 1, okay? If you're given the z-test statistic, if you're given a standardized value, okay? With a t, you're going to use t-CDF, okay? And you just have to enter the number and the degrees of freedom, which is given to, and if it's chi-squared, guess what we're going to use? Chi-squared CDF. All right, so so what we've got to do is we got to do normal CDF. Now, in this case, the alternative is greater than. So since it's greater than, I'm going to go greater than with my normal CDF. And so here we go. So we'll do normal CDF, which is on the distribution menu, which I go second vars, which is distribution, normal CDF. And so I go 1.7 to infinity. So, or you could just enter 9 billion. Just go like that. That's right. So there we go. And notice that, by the way, normal CDF automatically resets to 0 and 1 for that reason. Mean of 0, standard deviation 1. That's working with the standard normal curve, and that'll tell you the p-value given the z-test statistic. And there you go. So our p-value be 0.04456. So that would be statistically significant at alpha is 0.05. So that's how you do that. Now, if it was a two-sided test, by the way, you would have to multiply that by 2. But like, for instance, this. So a two-sided test means you're not just testing for greater than like we did here, but you're testing for outside of. You're testing for outside of. So if our t is 0.92, okay, the p-value is outside of that, okay? If it's one-sided, you just go in that direction. For instance, if this was less than right here, then you would go negative infinity to 1.7, you'd end up with a p-value of like 0.95 something. All right, so, but we'll do t-CDF for t, and we are going to go greater than. All right, so we shall say second distribution. So we're going to go t-CDF, and so we are going to go 0.92 to infinity to be outside of that. And our degrees of freedom is 25. And so we got that. So that 0.18, that is that area. But since it's a two-sided test, it's not just, you know, that big or bigger, it's also that smaller. It's also the negative 0.92 or smaller, which since it's perfectly symmetrical, that has the same area. So our p-value is going to be times 2. That's why we call it a two-sided test. So our p-value be that, okay? And then for chi-squared, since chi-squared is squared, it's always positive, okay? It's always positive. T and Z are negative half the time, all right? But chi-squared is always positive, and it's always right skewed. like that. And your p-value is always to the right. So if you have 5.68, your p-value is always here. So you'll just go chi-squared CDF. So you go second, vars, and you go to chi-squared CDF. There it is. We'll never use chi-squared PDF, by the way. So our lower value is 5.68. Our upper value is infinity. And our degrees of freedom is 4. And so that's 0.224 is our p-value. So we would not reject an almost any reasonable value for alpha. That's it. That is, that's roughly 35% of the course that I really just rushed through, but that's a quick rush through of most everything in inference. I encourage you to send me any questions that you have, and I hope you have a wonderful day.